Assalamualaikum and good day to Dr. Tamizi and everyone. My name is Sumaiyyah, and together with my teammates, we will be presenting our neural network mini project. For this project, we choose to do a deep dive into the computer vision domain, specifically analyzing the YOLO V7 architecture, which stands for You Only Look Once. To begin with, why is real-time object detection a massive focus in modern computer vision? Today, processing visual information at 30 fps or higher is an absolute architectural necessity for AI systems like autonomous driving and smart grids. Historically, developers had to choose between speed and accuracy. YOLO V7 completely shifted this paradigm. As noted in our report, it pushed the Pareto frontier by achieving massive average precision on the Coco dataset while running flawlessly at over 30 fps. How does it achieve this? The secret is the trainable bag of freebies. These optimization techniques improve accuracy during training without adding computational costs during inference, making YOLO V7 perfectly suited for real-world applications. This state-of-the-art performance didn't happen overnight. It is the result of decades of neural network evolution drawing directly into our course foundations. The journey started back in 1943 with the very first mathematical model in biological neuron, which eventually led to the perceptron in 1958. However, the propagation revolution in the 1980s is what truly enabled deep architecture design. For years, object detection relied on slow-to-stage algorithms like RCNN. The game changer came in 2015 when YOLO introduced one-stage regulations, making detection incredibly fast. Finally, YOLO V7 arrived in 2022. It incorporates these historical lessons into major structural blocks, allowing us to build deep networks without losing trainability.
Okay, thank you, Sumaya. Now I want to present about real-world application where YOLO V7 is used. You can see the domain and example use. So the first, we go to autonomous driving. Example use, pedestrian vehicle obstacle detection. Next is medical imaging, anomaly detection, diagnostic support. Next is robotic, object grasping, navigation. Next is surveillance, multi-object tracking and security. And last is smart grid. Example use is defect detection in renewable energy infrastructure. So next slide, this is about technical deep dive pen RAPConf. So you can see the pen reparameterization RAPConf, like traditional RAPConf include identity connection. They handle gradient flow in resident or concatenation network. So point 2 is YOLO V7's plan RAPConf remove identity connection, improve gradient propagation. So the benefit is during training, multi-branch structure for rich representation. During inference, branches are mathematically folded into a single convolution to faster execution. So this technique boosts inference efficiency without sacrificing accuracy. So now it's about technical deep dive ELN architecture. So the first we can see the extended efficient layer aggregation network ELN. The first we can see the problem, stacking many computational block later gradient paths and halting trainability. And the solution is use group convolution plus shuffle merge to expand block size while preserving original gradient path. So the result is increased learning capacity with stable convergence. So how it works? Feature map are shuffled and merged across group. Number 2 is existing gradient flow remains intact. And number 3 is the network scale deeper without losing trainability. So ELN is the backbone of YOLO V7, ensuring efficient gradient propagation.
Alright, thank you Rakib for the previous slide. In my part, I will speak about theoretical deep dive, level assignment, and loss function. So let's look at how YOLO Vision 7 learns this slide cover of two ticks which are level assignment and loss function. For the first one, for the level assignment, YOLO Vision 7 use a dual head structure which let head generate a fine grain, precise labels, and based on the ground truth. It help to early layers to learn, and we add a auxiliary head that uses sparse label with looser constraint, which can then improve a recall and stabilize the training and technique we learn about in lecture 6 as deep supervision. Second point is for the loss function. What is loss function? Is YOLO version 7 combines three components. CIOU loss handles boundary box regression. It measure overlap, distance, and aspect ratio. And binary cross entropy handles objectives and class probability. So the third point is assistant loss provide extra supervision, especially for the auxiliary head. In short, this setup allow YOLO Vision 7 to optimize for both precision and training stability seamlessly. Alright. For this slide, now let's connect to YOLO version 7 design choices to our course syllabus. This slide cover activation function and learning paradigms. For the first one, activation functions. In lecture 3, we learn about sigmoid function and their limitation, the vanishing gradient problem. YOLO version 7 solve this by using the SILU, which is a smooth, non-monotonic monotonic activation that keeps gradients flowing through the deep networks. It also uses a leaky RELU to keep gradient active even for the negative inputs. Additionally, batch normalization from lecture 6 stabilize training by whitening layer inputs, which allowing for higher learning rates. Secondly, learning paradigms. The delta rule from lecture 4 is a direct ancestor of YOLO version 7 SGD with momentum optimizer. The back of freebies technique like mosaic augmentation effectively increase the dataset diversity and improving model generation without adding inference costs. All of these operates through the same error correction principle we learned in the lecture 4 and but applied at the massive scales. In short, YOLO version 7 takes the foundation concept we learned in class activation, function, and gradient, descent, and error correction and scales them to the state of art level. Based on this, there is a limitation and future trend. For the current limitation, despite it have achievement, YOLO Vision 7 relies on heavily massive manually labeled dataset, which supervise dependency. And furthermore, the initial training phase incur immense computational costs, and the model remain susceptible to out of distribution dataset bias. For the future research direction, future paradigm look toward quantum enhanced training to optimize weight integration with self-supervised pre-training to reduce labor dependency and deploying lightweight ELAN architectures directly into a microgrid management and edge environment. So for the next part, we will show the demo using the notebook LM. Alright, from here, what I'm doing inside the Noble LM. First of all, I added 9 source of neural network lecture notes. So I upload in there. At the next part, I upload 3 academic papers in there. So in this prompt, I tried something to test it out. First of all, I'll try to make the summary from 9 lecture notes in here. So it give me the 9 lecture notes summarized: foundation, biology, architecture, learning paradigms, and single and multi-layer networks, advanced neural models based on each every lecture notes. So the next part for the 3 academic papers. So in here, you already say you already review the 3 academic paper, which I already provide it, and it summarize some of it like YOLO version 7, real-time object detection, blockchain assisted energy sharing, optimization and forecasting. Also the last one is interference and measurement quantum optimization. And then for the next one is I tried to get some info to easy related from based on track paper and from my lecture note. So it's already say based on summarize based on E-line and compound model scaling, plan reparation and cost finding. The next part is this is my prompt. I tried for section 3.0 cost integration and comparative analysis for my technical report. So what it gave me in here, it gave based on summarize for the actually 3.0 section. So what is it from need to do like technical report something and activation function, evolution there and learning paradigm and so on. So for the next part, explanation about notebook LM, I will pass to the RAQIB and SUMAIYAH.
For my part, I will share my screen to demonstrate on how we use Google Notebook LM as an AI research assistant. As you can see on the left panel, we upload 12 different sources. Um, these include all of our lecture notes and the research paper. Our goal was to see if AI could help us synthesize these complex domains. I used the audio overview feature to generate a 19-minute podcast from these files. What makes this tool so amazing is that it doesn't just read the PDF with a boring robotic AI voice. Instead, it sounds exactly like two podcasters casually chit-chatting with each other, breaking down the concepts directly from our provided notes. Because it feels like a real podcast, it became the perfect study tool. It allowed us to listen and revise complex neural network topics anywhere and whenever we wanted, like even during our leisure time or while commuting to class. They also find connections between our syllabus and the research. For example, in our report, we contrast YOLO 7 with self-organizing maps, SOMs, from Lecture 9. In this audio, the podcasters casually connect the unsupervised learning of SOMs directly to the decentralized blockchain microgrids. Let me play a short 50-second snip for you.
Pulling the strings. So we find the answer by analyzing systems that explicitly abandon top-down control, like completely. Meaning no central boss. Right. In traditional infrastructure, there's always a central authority dictating.
So now I want to demonstrate how Notebook LM can generate like quiz, report, meme and others. We can see the information and reference we can use to generate the slide and report. Now I want to show how they generate the report. We can see the introduction, 2.0 and the last of for reference in the report. Okay, next is the I want to show how can generate the technical quiz. You can see this example quiz. So next is research my map. You can see the research my map. So next is I will show the Fontaine distributions. So this is a comparison data generated from the data we have an end reference.